In this lecture, we're going to learn the basic graphing techniques, and these will be particularly useful on your lab graphs, sometimes for problems that you do in the textbook, but particularly for the lab graphs where you'll be required to make a full-page graph of your data that you've collected. And the basic technique works like this. You're going to draw a vertical and a horizontal axis, but you're going to leave yourself about 3 to 4 blocks from the edge of the paper, and the purpose for that, of course, is to leave room for your labels, the name of the property and the units, and then also for the numbers which will be running up the axis. So, for example, on this paper, I will take a ruler and come in about 3 to 4 blocks. And place my vertical axis. And my horizontal axis. Okay, and you can see that I've left about 3 to 4 blocks on either side to put in my labels. And that brings us to the second step, which is to actually place those labels. Now, in the case of this graph, the example that I'm going to make, I'm going to graph this data on the left-hand side. So on the horizontal axis, I'm going to have time in seconds, and on the vertical axis, I'm going to have the displacement or position in centimeters. So going down a little bit so that I leave room to write my numbers, I will write time in seconds, and then on the vertical axis I'll write displacement in centimeters. Okay, and you'll notice that I placed those at about the midpoint of the graph on both the vertical and the horizontal axis. There are also examples in which, besides the units, you may use a multiplier. So typically speaking, in a graph, you generally don't want the numbers to go above maybe like 100, or at least not in any more than the low 100s. So maybe 200 or 300 might be fine. But if the numbers start getting up into the thousands or higher, let's say into the hundreds of thousands or millions, it's better to make a multiplier in the label. So I might add something in here which would say displacement parentheses times 1,000 centimeters. Or I can also use the slash. So there's two potential ways of labeling these. You can use either one. This is the preferred method for the IB, and generally in the United States this is the preferred method. But either one would be acceptable. And if the numbers are very big, we're going to reduce the numbers that we have to write on the axis by putting a multiplier in there. And I'll show you an example of that in just a little bit. In our example here, the data only goes up to a little less than 25 and no bigger than 10 on the horizontal axis. So there's no reason for us to use the multipliers for this particular graph. Okay, those steps are pretty easy. The next step is to determine what the value of one block is going to be. And that can be a little bit tricky. So, for example, you want to look at the highest data point that you have. And on my data, I had 10 for my highest on the horizontal axis and 24.6 on the vertical axis. So you want to figure out how much one block is going to be worth, keeping in mind that you want this graph to take up at least half of the available space, both vertically and horizontally. So in the vertical direction, I want to make sure that I get at least to about here, the midpoint. If my graph is smaller than half of the paper, then obviously I could have just, for example, doubled everything, and that would have stretched my graph out. And same thing horizontally. If my graph comes out in a space that's only about this big, then I could have doubled everything, and that would have brought my graph out to about here. And the purpose of making the graph a full page, of taking advantage of both horizontally and vertically the entire page, is that number one, it's easier to plot when you're trying to put the points in the first place. And secondly, when people go back to read your graph and they're trying to find values off of it, It's much easier to read the bigger the graph. I mean, I think that's pretty obvious that you have an easier time reading large graphs than you do trying to read a small graph. And most of the time you have to read between the lines. Well, it's very difficult when the graph is compressed down into a small section. So we want to stretch this graph as much as possible. And to do that, you want to make smart choices. So let me give you, for the example of this graph, I've already counted the number of blocks. Horizontally, I have 38 blocks from my origin to the edge of the paper, and vertically, I have 50 blocks from the origin to the top. Okay, so for example, let's do the vertical axis first. And so in this example, I want to get up to a maximum value of 24.6. So what I would do is take the 24.6 and I would divide that by the number of blocks that are available, and that is going to be 50. And that tells me that the most that any block can be is 0.49. Any bigger than that, and my highest data point is actually going to come up off the graph. So what you're going to do when you divide the maximum value by the number of blocks available, that tells you how much one block is worth, and you're going to go a little bit bigger than that. Now this one worked out really nicely, because that means if I just make it a little bigger, if I make each block 0.5, then I'll easily be able to make it to the top of the graph paper, and my top data point is not only going to go past the halfway point, but it's going to be right up near the top edge, which is exactly what I would like to see. So in this case, we're going to make each block worth 0.5, but one of the really important things that you want to make sure to do, and I've listed that as step 4, is you label the axis, of course, but you don't label every block. That's too cluttered. There's no reason for you to have labeled every single block. So instead, you're going to at least skip every other block, maybe every third block, every fourth, maybe even every fifth, probably not more than skipping 5 blocks. I mean, look, if I label this, we decided that each one of these blocks was going to be 0.5. So if I label 0, and I label this one as 1, and this one as 2, I mean, is it really challenging for you to recognize that this line must represent 1.5? It doesn't really require any calculation on your part. It's very easy to tell that this must be 1.5. And there's no reason to label 0.5. One, you end up with a graph that ends up looking very cluttered, and you want to keep this axis looking clean. It's actually easier to read if you don't put the extra labels, the 1.5, the 2.5. It just makes a much cleaner looking graph. So I'm going to finish this, and then I'll come back to do the horizontal axis. Okay, so if we take a look now, you can see that I've labeled my graph. I skipped every other block. I labeled every other block as 1, 2, 3, 4, and it took me up to 25 at the edge of the paper. And remember, my top data point on the vertical axis was 24.6, so that's perfect. I got right up to the edge of the paper. So now I need to deal with the horizontal axis, and on the horizontal axis I need to make it up to 10. I've counted the blocks, and I have 38 blocks. So if I use the same technique that I used just a moment ago, that means that I would take 10 and I would divide that by 38, and I get 0.263. Now that's a little inconvenient. If it had come out to be 0.25, that would have been just perfect, and I could have gone right to the edge of the graph. So again, remember, you're always going to want to pick a number a little bigger than that for the value of one block. Now in this case, what I'm going to choose to do is to make each of the blocks worth 0.3, but I'm not going to label every block as 0.3. Again, just like I did with the other one, I'm going to skip every other block at least. So my first block will actually be marked here as 0.6. Again, it's not terribly convenient, but if you think about this, if this portion right here is 0.3, that means every third of a block is 0.1. That's not great, but it's not that difficult to imagine this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. You can visually estimate where about a third of a block is, and each one of the thirds of a block is 0.1. So when I continue on with the next one, this will be 1.2, and I'll go ahead and finish this, and then we'll come back in just a moment. Okay, so now I've finished labeling my axis, and you can see that I ended up with 10.2 is my highest label on the axis, and it's pretty close to the edge of the paper, well beyond the halfway point. So my final point is going to be right about here, about a third of the way through this block. This middle point right here is going to be 9.9. So I'll go a third of a block right there will be my last data point. So everything is stretched out. I've got all my labels in place. The next thing to do is to go ahead and plot the points, very carefully. Make sure you take your time. There's no rush. Make sure you get them in the right place, because to have to replot the data points means that you're going to have to erase, and then the graph is going to start to look really messy. And you would like to be able to do this in one shot. Just as I did with the axis, I took my time. I carefully thought about how much each block was worth. I'm going to do the same thing with plotting the data points. So, for example, my first data point is here at 1.0 and a vertical value of 2.2. So I know that 1.0 is going to be, right here is 0.9. Between 0.6 and 1.2 is 0.9. So I'm going to go about a third of the way. I'm going to slide up here until I get to 2. At this point I'm at 2.5. I want 2.2, so that's going to be just slightly below that point, and I'm going to plot the point. Okay, so I'll go ahead and continue to plot the points, and then I'll come back and we'll go on to the next step of our graph. Okay, so at this point I've plotted all the points. So let me slide up and let you see where my last point goes. And the next step, once all the points are plotted, is to decide what kind of trend line, what kind of best fit line do we need to put to this thing. And there are two possible choices. So let me put the notes in here now. Okay, so step 6 is to draw a best fit line or curve as the data dictates. So if the data appears to be straight, then you draw a straight line using a ruler. And if the data appears to have a curve, and the curve might be subtle, but if it has a curve, then you're going to have to hand draw a smooth curve. Most important thing about drawing the best fit line is that you never ever connect the points. Okay, the data has scatter. You can clearly see that my data does not form a perfectly straight line, but the general trend is a line moving up to the right, and there's no real indication that there's any sort of curve to it. So what I'm going to do is to put the ruler down and follow the trend. I'm not going to connect the dots though. Okay, all data is imperfect. The reason why the data jumps around a little bit and doesn't follow the perfectly straight line is not because the physics doesn't show that it's a straight line. It's because of errors in the measurement. And we've talked about the errors that can occur in measurements, the reading errors, the random errors. Those kind of things will cause this little bit of random scatter, and as a result you are going to sort of create the trend that the line produces. And once the line is in place, the line is more meaningful than the data. In essence, the line becomes the only important thing once we draw it. And so basically I'm going to take a ruler and do my best to try and find a location where I can draw a line that is going to sort of get some of the data on one side and some of the data on the other side. So I would say that somewhere about here. Now if you're not 100% sure, a good idea before you draw the best fit line is to draw it in pencil first. Do a light line in pencil, and what you want to see is data going back and forth. Some data's on this side, some data on this side, some on the other, going back and forth. So I see the data kind of scattering back and forth. I don't know, my trend line might be a little bit off. I might have been able to slide this trend line down just a little bit to get it to fit the data a little bit better. But you can see that if I start from the beginning of the line, that the data kind of scatters back and forth across the line. But I don't connect the data points individually. Okay, so at this point we've nearly completed the graph. We have just about everything that we need to do. Depending on what you're being asked to do, if it's a straight line, it's a very good possibility you'll be asked for the slope of the line, or you may be asked for other information regarding this line or the graph. And I won't put that in here because that depends on the circumstances. But what you generally would want to do is you do want to put a title at the top of your graph. Now you might wonder why I waited until now to put that title in, and the reason why I waited was to see where my graph went. I may have had a graph that went up and down, and I may have needed the middle portion here, in which case I would have put the title off to the right or maybe a little bit to the left. But as it turned out, in this case, I have a nice open space here near the top of the graph, and so I'm going to call this my displacement versus time graph. You might underline it or highlight it, put a box around it. And in essence, that completes the graph. Now, some teachers, and it depends on the teacher, but some teachers might actually want you to put the data table on the actual graph. It's kind of a nice way to have everything all in one place. Instead of the data tables in one place and the graph is in another place, you could copy the data table onto the graph. Now, how would that work? Well, you, in essence, all of this empty space here is not being used at all. So what you might do is draw a neatly organized data table and then transfer the original data table onto here so that you have the graph and the data table all in one place. And I'll go ahead and do that right now to show you how it looks. Okay, and so now I have my completed data table, and I've finished the table up here in the upper left-hand corner. I could just as easily put the table down here in the lower right, but you basically need to decide where the data table is going to go after you've already made the graph and you know for sure where you're going to have some empty space. There's really no reason, for example, if I want to read the graph, I can still read the graph by just going right through and ignoring the data table. So it doesn't really affect my ability to read the graph, and it's just a nice way of sort of completing the graph by having the original data table on there at the same time. In addition to that, then if I were going to make calculations of slope or other things on the graph, I would just be as likely to put that on the graph somewhere else down in the empty space, and I would just make sure to very clearly label it. I would do all my work beforehand so I know exactly what I'm going to write so that the graph still looks nice and neat and organized, not just some sloppy calculation thrown off down at in the bottom right or in the upper left-hand corner. And essentially that's it for our straight line lab graph. Now, as I pointed out, not all the data will be a straight line. Sometimes you will have data that has a subtle curve to it. And so I have a second set of data, and I've already made the graph. So I took a second set of data, and for this particular one, I had to make it up to 110 on the vertical axis. So one of the things that I did was to count the blocks, and in this case, it turned out that the wisest choice was to make each block worth 2.5, so that when I counted every other block, I was counting by fives, 5, 10, 15, 20, rather than the example that I showed where I counted by ones all the way to the top. I ran in on the vertical axis. I had to make it up to 5. Again, I ran into a kind of a difficult situation, so I ended up making each of these guys 0.3, and so I sort of think of this as one big block, and that means that every third of these two blocks would be 1. So approximately 0.1 is here, 0.2 is there, and then 0.3, 0.4, 0.5, 0.6. It's tough. I wanted to make it all to the top, though, and my final data point is at 5, so that means I made it all the way up to here. Let me zoom out just a little bit so that you can see how the data actually looks. And it's pretty clear that this one is following a curve. I mean, there definitely is an upward curve here. In this case, this one's probably forming a parabola. And so what I need to do for this situation, I can't use a ruler for this, I need to hand draw the curve. And so for this circumstance, what I find easier is instead of drawing the curve going away from myself, I tend to find that it's easier if I draw the curve, whether I go right to left or left to right, but to draw the curve so that my hand can move like this. And so I'm going to do my best to try and draw a curve here. Again, it would be really wise for you to take a pencil and just very lightly try to draw it in. And if you find that the line looks good, then you'll go back and darken it in with a pen, or just darken in the pencil line. Okay, so that's not perfect. If I were going to turn this in as my final product, I probably would redraw that line again. There's a few places in here where my hand sort of wiggled just a little bit. But for our purposes right now, we'll go ahead and finish this graph off by darkening this in with a pen. And I will do my best to smoothly follow the line. Now, one thing you're going to see is that I'm going to, at all costs, and you can see I'm getting a little off my original line, at all costs, I'm going to avoid doing what I just did, which is to avoid picking up the pen and making one smooth, continuous line. And then obviously at this point I'll go back and I'll erase out my pencil line. But ultimately what I'm trying to avoid is something like this spot right here, where now it becomes a little difficult to read the data point. If I, for example, wanted to know at 2.1 what the value was by reading the line off the graph, it's a little difficult because I made this little mistake right here. So what I would ideally like to see is one smooth continuous line going all the way up. What a lot of people do when they have a curve like this is they tend to try and make the line looking like this. Okay, and this is not an artistic representation of the data line. It's supposed to be a data line, a single solid line, continuous and smooth, not this feathered sort of look. So make sure that you avoid doing this kind of thing. You do get a good fit. You can find that if you go back and forth like that, it might seem like the fit looks better, but how do you read the data point here? I mean, look at the line. There's 3 or 4 lines right there. How do I know which one to read if I'm trying to read off a value? So if I slide up at 2.1, I mean, where exactly here am I reading? These lines cross the 2.1 value on the horizontal axis at about 3 or 4 different places. So you really want to avoid that feathered look and do your best to make a smooth, continuous line. Just as we did with the axis and we took our time and we made sure that we plotted it out ahead of time, redraw the line several times if you need to until you feel like you've got a good line, and then smoothly take that pen, or if you want to just darken it with pencil, and draw it in so that you get a smooth continuous line. And that's going to allow you to make your measurements or make any readings that you need to off the graph much easier. And that's basically it for the basic lab graphs.